In this video lecture, I will discuss how to select the number of factors in vector-augmented regression models. So we start off from where we left off in the previous week. We consider a high-dimensional regression model where we have a high-dimensional matrix X plus possibly a low-dimensional matrix W of variables that we want to include anyways. And to deal with the high dimensionality in X, we assume that X is driven by R common factors. But these common factors are latent, so we do not actually observe them. This allows us to write a vector structure for X, where we can write X as the factors times the loadings, which indicate how much of the factors actually load on each of these variables in X, plus some idiosyncratic error terms that are unique to each individual variable. Then, if we would substitute the expression for X into our high-dimensional regression model, then if we rewrite things, we can write Y as a function of a low-dimensional F, so R is assumed to be small, plus a low-dimensional W, plus an error term, which captures not only the original error term, but now also the part that we cannot actually capture through the factors, so the idiosyncratic components. So if we could estimate this model and we would know R, then we would have a low-dimensional standard regression that one could easily estimate. So we're going to take the last one as our starting point. So we're going to directly write Y as a function of F and W. And we're going to, well, as we already did, we looked at how to actually estimate F from X. That's what we did when we studied principal components. And then once we estimate, we have estimates F hat, we can plug those into our regression model. And this is a low-dimensional regression model you can easily estimate. But of course, the main thing that we did not actually look at is how many factors should we include. If we don't assume that factors are known, then why would we know how many there are? So what we have to do in practice is to estimate this. And for that, what we do is essentially look at the fit of our vector model. So we define just a residual sum of squares as we would do for a standard regression model. Except of course now we actually both have the lambdas and the f's which are unobserved. And I'm going to write here explicitly R superscript in parentheses to indicate that these are the factors obtained by fitting R factors. Now, you might want to minimize the residual sum of squares to maximize the fit, but it's like these squares, the more variables you add, in this case the more factors you add, your fit will become better and better and your residual sum of squares will decrease. So this of course is not a good solution because it will lead to overfitting, but it is of course a standard situation that we can handle, and in fact what we can do is use information criteria to balance the loss of fit that we measure through residual sum of squares and how many variables we actually, in this case how many factors we actually include in our model. Now, information criteria here are slightly different because we have two dimensions to care about. We have n and p, so in a standard regression setup you only have n. Here we know that both n and p are increasing, so they should both come back in our information criteria. Now there's been a whole lot of literature on information criteria. What I'm going to discuss here is the first paper, the one that pioneered them, by and Eng in 2002. Since then there are lots of variations, but still the ones from By and Eng remain the most popular in practice. They come up with two different kinds of information criteria. So the one most familiar is the one on the right, which they call IC, which takes the log of the residual sum of squares and then adds k times a penalty function, where k is the number of factors that you are including. They also have a different form which is not based on logarithms. In fact, this form also exists for the standard information criteria, so you don't take the log. The log implicitly assumes normality. The other one does not, but the disadvantage of that is that you have to estimate somehow the variance of your idiosyncratic components, which they propose to do via fitting a certain maximum number of allowed factors. Now, depending on the on the penalty function that you choose here, the g, you of course get different information criteria. Now what they show is that if you have a penalty function which converges to 0 when n and p go to infinity, and also when you multiply it with the smallest of n and p, it goes to infinity. So this provides both a lower bound and an upper bound on how fast it can grow. Then we actually can consistently estimate the true number of factors. So we minimize these criteria, pick out the number that minimizes them, and that will be a consistent estimate of the true number of factors. Now they consider 3 different functions which all satisfy these criteria, which then of course gives you in total 6 criteria. So, I mean, in principle, in theory, they are all equivalent. Obviously, some have stricter penalty functions than others, and it's like we have in regular information criteria, depending on what penalty function you choose, you can either go for being more strict or allowing for more factors to be selected. There is not really any strong preference for one of these 6. I think in general, people usually use the IC criteria and hope that actually what you get from the 3 criteria is relatively close to each other. There's another way to do select a number of factors, and that is by looking at so-called scree plots. And scree plots are a graphical way, they are very old already, that we can investigate at least eyeballing how many factors we would need. So what we need for that is an r squared, and a specific r squared for the jth variable. So we calculate the r squared only based on essentially the regression for the jth variable. How well does your factor model fit? And then you average those r squareds over all variables. What you then do is you plot this average against the number of factors, and in particular what we do is we plot how r squared evolves if we add another factor. So we plot the difference between adding k plus 1 factors and k factors. So what we then basically have on the vertical axis is how much is the fit improved by adding another factor. And what we then want to achieve is to see where in this plot is there a kink. And the idea is before the kink, your fit is improving considerably, but after the kink, it's not anymore. And at that point, you've reached the number of factors that explains enough of the variation in x. Now, we can interpret this scree plot in a different way. So we do a bit of rewriting using the same ideas as we did for principal components. First, we're going to rewrite the entries appearing in the residual sum of squares. So if you write out this L2 norm, we can write it out in just quadratic form. Plug that in your squared, and then realize that actually what you have in the denominator here is xj prime xj. So we write 1 as xj prime xj divided by xj prime xj. And then we can see that actually xj prime xj cancels out against this one here as well. So we're left with a simpler expression. Now, suppose we standardize our data, which is something you typically do before you apply a factor model. If not, then we can always standardize within these expressions. But if we standardize, then the xj prime xj is equal to n. So we can replace dividing by xj prime xj is dividing by n. So we can n squared here. We don't have a fraction anymore. And then we realize, as we did for principal components, that this sum actually is equal to the trace of this matrix. And we know for the trace that actually the trace of A times B is the same as the trace of B times A. So we can swap the matrices around, exactly like we did when we derived the principal components estimator. And then realize that the trace is nothing more than the sum of the diagonal elements. So we've done the same argument as before, exactly the same. And so you already see the similarities that we end up with compared to what we did when we derived the principal components estimator. Well then, that's the final step. note that your factors are, if you estimate them by principal components, are the elf factor is the eigenvector corresponding to the elf largest eigenvalue. So we can replace the expression that we have in here, x prime times f, by just the eigenvalue times the factor. Note that these capital letters f here should actually be small letters. They are the same as those here. So we're just using the eigenvalue property. Well, then we also know that by the way that we standardized in principal components, the way that we identified our factors, that they should be orthogonal and particularly FL prime FL should be equal to n. So this whole expression of the average r squared is nothing more than an average of the eigenvalues, the kth largest eigenvalues of the matrix x prime. So instead of drawing this r squared, we could also draw eigenvalues. So we would draw the k plus one largest eigenvalue against k. And so again, the idea is the same. What we do is we want to find out if the eigenvalue is large. This is evidence that there is indeed a factor, and so we would expect that if there are k factors, then after the kth eigenvalue, we should observe a drop in the eigenvalues. So again, we're looking for a kink in this plot of eigenvalues. Now, of course, doing it visually is a bit up to interpretation, and you might not always get a conclusive answer. Now, there are also methods proposed by Wernatzky which take this idea of eigenvalue comparisons and provide formal methods where you can actually use a formal method to determine the number of factors based on this. Now, let me just give you an idea of what this actually looks like. So what I did here is simulate a DGP where there are no factors. So actually my x's don't have a common factor structure. Now what we see if we look at this creep plot is that there does not appear to be a kink anywhere. So this is an indication that in fact there's nothing here that's really explaining a lot. You can also see it by looking at the axis, where even for the first factor it only explains 3.8% of the variation. And in fact, if I do information criteria, I look here at IC2, I get 0 factors. So that's a good case, right? We would indeed pick up that there are no factors. Now I put in one factor and I put in one strong factor, which really explains a lot of the variation. And you see that in this idealized case, this creep plot is super obvious. You have a massive r squared here for the first factor, and then it drops pretty much to 0. So you have a very clear kink at 1. Of course, given this is so obvious, the information criteria will also be able to pick this up. Now I do a weak factor. So again, there's one factor, but the factor is not as strong as before. So it's considerably weaker. And in fact, we see that the y-axis here only goes up to 0.14. So the first factor explains a bit more than 0.14, whereas here it goes up to 0.8, which is really an extreme case. Now, you still have a very clear kink in your squeeze plot, and again, your information criteria also picks this up. Now I put two factors, again, two relatively weak factors, but still everything works quite well. So we really see this kink nicely here in our squeeze plot, and the information criteria also picks up the right number of factors. Now this is a case where, for instance, things become more complicated. So here we have one strong factor and one weak factor, and this strong factor is so much dominating that it appears as if the kink is here at 1. In fact, you have a second kink here at 2, but this is hardly noticeable, and it's only because I know that there are 2, I actually would recognize it as a kink, but I think everyone would go for 1. And in fact, also my information criterion goes at 1. So here we have a case where one of the factors is so much stronger than the others that it really dominates, and in fact, the second factor, you would barely need it according to these methods. Now, of course, this is a very stylized example where I simulate a very simple DGP. What we'll often see in practice, I will come back to that in a later lecture, is actually that the information criteria tend to select a lot of factors. So rather than having this very few, you tend to have quite a lot, and often it's close to your maximum number that you allow for. So this is something which is strange, that in practice it seems to perform much worse than in simulations. Now let me finally comment on one thing that we have been doing so far, and that is that we've only been determining factors and also the number of factors based on how well they explain X. But in the end, we're not so much interested in explaining X, but we're interested in explaining Y. Well, obviously, if we believe that X affects Y, then clearly if we can explain X, we can also explain Y. But we might be better off to directly try to explain Y. So rather than finding factors in X that explain X, we could try to find factors that explain Y. I mean, in principle, you could have a case where the major factor that you have in X does not even impact Y at all, and it's actually the second and third weaker factor that are influencing Y much more. But maybe these factors you would not pick up, because we've seen that, for instance, the discrete plot might let you think that there's only one factor. So this could clearly be a problem. And this is an example of where what we're using is unsupervised learning. So we're trying to find patterns only in X without a target to go to. Supervised learning, on the other hand, is takes your series that you want to explain, your Y, and then tries to fit a model that best explains that Y. So in machine learning, these are two different categories of learning methods, of statistical estimation methods. And of course, they matter depending on what our purpose is. Now, how could we address that in a factor setup? Well, one thing you could do is say, well, I'm going to put in a lot of factors. So I'm not just going to put in the factors that are my discrete plot picks up, but I'm going to put in a lot more factors. And maybe even all. Maybe I want to even put in all possible factors, which is the minimum of N and P. And maybe I also want to put lags actually of these factors, because who says that the lags could not also influence Y? But of course, then we have again a high dimensional problem, so we cannot evaluate that using standard methods such as BIC and AIC. Now, of course, you can think of ways to reduce the dimensionality, saying we only include a lesser factor if the more important factor is included. Well, it's hard to argue a priori that this would always be the best. Now, of course, there are methods which actually do this, and one of them is the method of partial least squares, which is really an extension of least squares, but allowing for factor kind of models where we really find factors directly that explain Y rather than X. Now, of course, another thing you might consider is, well, if I have this big regression here with all these factors in, this is just a high dimensional regression model. Why should I not use the lasso or some other penalized regression method to select my variables in there? And that, of course, is also an option. Now, we have looked at how to select a number of factors. So we now we would be able to apply our factor model in practice. So what I will do next in the next lecture is have a look at the assumptions that actually underlie this factor model. When can we apply a factor model, and when can we not apply a factor model? And then afterwards we'll have a look at a bit of intuition for the asymptotic theory of factor models.